to the world of 3D printing. Thank you all for coming this evening. I really take pride and actually joy in recognizing our sponsors, and I've been very, very negligent over the past several months in that I have failed to recognize probably 3 of our best sponsors in the sense that not only they support us financially, but they support us with their time on the MIT Enterprise Forum. And that would be Dave Cronin. I didn't see him here, so I guess he's not here, but Dave is Vice President of the Bank of the West and is also our treasurer. Ben Tucker of Merrill Lynch. Ben, you're here somewhere. I know you are. There he is in the back. Ben is our event chair and is responsible for putting on all of these events. And then Paul Meyer. Where's Paul? Raise your hand, Paul. You're around here somewhere. Well, I don't know where he went. I saw him earlier. Anyway, Paul is our secretary. So if we could give all of those 3 guys a big hand. Appreciate it. Now, we're fortunate to have 3 great speakers tonight or this evening. And but before we get into that, I wanted to mention that we also have, in addition to the 3 planned ones, we have an unplanned one here. Peter Lombroso. Am I pronouncing it wrong, right? Lombroso, could you stand up? Peter's from 3D Systems, which is one of the, well, probably the big dog in the 3D printing space. And oh, by the way, if you haven't already, sometime this evening, be sure and take a look at the table up here. There's a lot of exhibits of 3D printed products, and including some that Peter brought. They're truly amazing, and I think they'll be worked into the various presentations as we go along. Our 3 speakers tonight are Brian Jaffe, Casey Hare, and Donald Park. So to start with, Brian Jaffe is Mission Street Manufacturing, and Brian got his bachelor's of science degree from Princeton in mechanical and aerospace engineering, and then joined the Navy, where he worked on the nuclear Navy, where he was working on nuclear vessels. Went back to MIT, MIT Sloan for the MBA program. In his own words, he got simply too turned on by the 3D printing experience he'd had as an undergraduate at Princeton, and didn't want to just stay in school. He wanted to make it happen. So he founded Mission Street Manufacturing. So with that, turn over to Brian.
All right, so first off, thank you everyone, and thank you Craig for the introduction and the whole MIT Enterprise Forum. I'm actually new to town, as Craig mentioned. I just took an indefinite leave of absence from MIT in June and moved out here. I figured if I'm going to work for myself, I might as well do it someplace as beautiful as Santa Barbara. So it's great to be here, and everyone has been so welcoming, so I really appreciate that. The title of my presentation, as you can see, is why I love 3D printing, and I really do love 3D printing. I'm one of those people that gets to do something I love every single day. I hope all of you are those people as well, but I'm one of them, and I feel very fortunate. But before we get started, I kind of want to, you've heard a little about who I am. I'd like to hear a little bit about who you are. And so just kind of by a show of hands, I'm trying to get a sense of how much people know or have experienced 3D printing so far. So how many people have heard of 3D printing more than a year ago? Okay, how many people have read at least 5 articles about 3D printing? Excellent. How many people have seen a real 3D printer? How many people have used a 3D printer to make something that they have designed themselves? Okay. So as you can see, a lot of people have heard of this technology, and yet not that many people have actually had a chance to use it. And that's what I want to change, and that's what Mission Street's trying to change, is hopefully in 3 to 5 years, every one of you will be raising your hand to that last question. But so here's what I'm going to talk about today. Craig asked me to give kind of a brief history of the technology, and then I'm going to talk about my 3 favorite applications of 3D printing. Now there are dozens that are just absolutely mind-blowing, but I'm only going to touch on 3 of them. And then finally I'll conclude with why I think 3D printing is going to change the world. So to begin, where does 3D printing really exist in our history? To me, it is what sets us apart from the animals is that we make tools. And the thing about 3D printers is that they are the most powerful tool, I believe, we've ever made, because it helps the individual make their own tools. For instance, your car is a tool you use for transportation, or your phone's a tool you use to communicate. But all of these tools had to be made by something, and usually they're made by some far-off factory in China. And I think that what the promise of 3D printing is to bring that power, even in a small sense, back to the individual. So that's why I think it's really one of the most exciting technologies that's ever been invented. But what is it exactly? So 3D printing has gone by a few different names. One is additive manufacturing. Another one you've probably heard is rapid prototyping. But really what it is, for those of you that have not had experience, is it's a way of making a three-dimensional object. Like, for instance, this elephant here. So what you do is you slice a three-dimensional, this would be a file in a computer. And then what happens is this gets sliced up into a bunch of tiny micro-thin layers, and then some process makes each one of these layers one on top of the other. And the two most well-known, or the oldest, are stereolithography, known as SLA, and fused deposition modeling, known as FDM. So SLA is basically a process where there's a liquid resin and a laser cures one layer at a time. And then fused deposition modeling is more like a hot glue gun that's being driven by a computer. And then it lays down a path that constitutes one layer, and then kind of the bed goes down and it does the same thing on top of it. But as you can see, I mean, with a shape like this, what this really is probably a couple hundred individual layers that have all been fused together. And so if you were to look at it under a microscope, it wouldn't look smooth, but from a distance, this is a pretty smooth part. So that's kind of how the technology works. The history of it, 3D printing is actually older than a lot of people imagine. It's almost 30 years old. It was founded, or it was invented by Chuck Hull, the founder and chief technologist, I still believe, although I should refer to you, of 3D Systems Corporation, which is the biggest 3D printing company. And yeah, 1984, and then in 1986 is when he founded 3D Systems. In the 90s is when it really kind of got going commercially. And it was known as rapid prototyping. In fact, the term 3D printing, I think, didn't even come along until the mid-90s. It was used by major industrial players as a way of, hey, instead of spending a ton of money making this new medical device and then finding out that it's wrong or it doesn't fit in people's hands the way it's supposed to, we can test the look and feel in a much cheaper way before we spend tens or hundreds of thousands of dollars on tooling. That's essentially what the technology was used for in the 90s. But then something very exciting happened in 2005, and that was the RepRap project. RepRap actually stands for, or it's a shortening of self-replicating rapid prototyping machine. What it was is some of the early patents expired, and a group of researchers at Bath University in England got together and said, we can make a 3D printer that is open source, meaning nobody controls the IP for it. Everyone can kind of share in the design of it. And a whole community came out of it it was really called the RepRap project, and it still exists today. And what this developed was a common set of both software and hardware designs that all of the low-cost 3D printing machines today are based on. So how many people have heard of MakerBot, for instance? So MakerBot is actually just a RepRap variant. They basically put together these RepRap kits. They found that the kits themselves had some flaws. They improved on them, but their software that ran it and really the design that MakerBot's based on can all be traced back to RepRap. And then finally, I would say today is kind of a turning point, and it's because finally the cost of 3D printing is getting down, of really low-end 3D printing is getting down that everyday consumers could imagine buying one for themselves. I mean, I first saw 3D printing in 2006, and it blew my mind. But this was a $20,000 machine. And no matter how cool it was, I wasn't going to not buy a car and buy a 3D printer instead. But today, there are kits that you can buy for just a few $100s. And there are fully assembled 3D printers you can buy for under $1,000. And so what you can see is that the price of the cheapest 3D printer has come down just dramatically. And very quickly it will be effectively, well, it won't be zero, but it will be effectively within the price range of anyone who actually wants one. So what makes people decide whether or not to participate in 3D printing is not going to be so much, well, can I afford it, but what do I want to do with it? And I think this is a big shift, and I think this is going to give rise to true consumer adoption of this technology, but maybe in less expected areas than the traditional rapid prototyping or engineering uses they've been applied to in the past. So that's it for history. Is everyone still with me? Okay, I promise there won't be a test or anything. So the next thing I'm going to do is talk about my 3 favorite applications of 3D printing. And the first 2, I'll be honest, I have nothing to do with. I'm just a fan. Like I said before, I love 3D printing. So the first one is topology optimization. So that's like a huge mouthful. I recommend not saying that 5 times fast. But what it is it's a computer-driven simulation technology that allows you to take apart, for instance, this hook, and analyze it for the forces that are on it. And what it really does is in the computer model, it will break this part up into thousands or millions of different tiny little pieces. It will analyze each one of these pieces and find out which one is the least important. And it's a game kind of like Survivor. So that piece gets thrown out, and then it does it again. And then the next least important piece gets thrown out. And this process is repeated over and over and over again until what you can see in the bottom right in that blue, you end up with something that is just a small fraction of the original size and shape. Well, it's the same outside shape, but it's a small fraction of the original material. I was going to ask, what does that sort of look like to people? Does that look like anything? Does it ring any bell, like the structure of that? It's kind of odd looking, right? Like bones, exactly. So if you think about it, the process that topology optimization is doing is pretty much the same process that's happened within human bodies over thousands or tens of thousands of generations. If you think evolution, we basically found, well, that part of the bone is not very important. So if it's not there, we are still going to be able to walk around and function. So really in the same way that evolution has optimized skeletons or exoskeletons, this process uses computing power to do the same thing. But the problem is that last shape there on the bottom right is too complex to manufacture. So the last step, and you can see the little gray hook there, that's what people have had to do. They almost have to put a fix on it and say, well, maybe that one's perfect, but we can't make it. So we have to change it back to something we can manufacture. But what's exciting about 3D printing is a shape like this, for instance, would not be able to be machined using modern machining tools. But a 3D printer can print it just as easily as it could print like a simple gear. Because in the world of 3D printing, complexity doesn't cost you anything additional. So this is just as difficult to print as a very simple part. And I think what topology optimization is going to do is allow us to, the structures of our cars, they've already been using it in airplane wings where, if you can save a couple pounds in an airplane wing, that'll translate into thousands of dollars over the course of the airplane life. You're going to see a lot of advances in structural design because all of a sudden things that we couldn't make before using 3D printing is now possible. So topology optimization, my 3rd favorite application of 3D printing. My 2nd favorite application is 3D printing buildings. Now, maybe this is because my father's an architect, and so I've grown up around building sites my whole life. But there's something really amazing. I mean, it's neat to be able to make little gear mechanisms like this. So I have lots of fun making these things all day. But what's really cool is the idea of making, housing or office buildings or temporary shelters. Construction is still one of the most labor-intensive and least efficient manufacturing activities that humans do. And 3D printing could potentially really improve efficiency there. This is a research group out of USC, and this is a research group out of MIT. This is the MIT Media Lab. Now, this is even neater, but it needs a little bit more explanation, I think. On the upper left, you see basically a robot printing, or 3D printing, but on a very large scale, using what's actually a foam. It's like a foam, kind of like think of spray paint can, but it's just putting out foam. And what it's doing, I mean, a foam doesn't make a very good building, but what it can do is it can hold, it can be the mold within which concrete is poured. So what they could do is basically 3D print this concrete mold and then pour the concrete in the middle, and boom, you have a building. So what's this thing on the bottom right doing? People have probably seen that watching football before, right? It's the Skycam. So the people at MIT said, you know, this foam, this little can of foam isn't very heavy. It's about the same weight as maybe the Skycam. So what we could do is we could use the same technology that's using to drive the Skycam around the stadium, and we could just attach this little foam dispenser on the end of it. Now we can 3D print something truly huge, and the only structure we need is just 4 posts in the 4 corners. You could print something the size of a city block. So again, I just think this stuff is fantastic. I don't work on it at all, but I think it's amazing, so I thought I would share it with you guys. But lastly, my favorite application of 3D printing actually is what I'm working on, and that is making 3D printing accessible to the next generation of designers. So if you can't read this, this is a Play-Doh 3D printer. This was actually a spoof. It's not a real product. I did kind of have a heart attack when I first saw it. But now this was an April Fool's joke last April. But it got a lot of people, and then there was a whole strain of comments at the bottom of this thing that said, like, oh man, I would totally buy one of these. And the joke was it only prints as fast as your kids will crank the little cranker lever. But essentially, this is what we're trying to do. We're trying to say, you know, the most creative people among us are actually children. Because, I mean, imagine it. Put a kid on this beach, and he's going to make a sandcastle. You know, take a kid to the snow, he's going to make a snowman. Kids love to play with Legos, with Play-Doh. Kids are inherently very creative creatures. And I think that 3D printing is just tailor-made for children, young people who want to be expressive, want to build things. And so that's what we've set out to do at Mission Street. So first I need to talk about kind of why this isn't being done today. And what I'll walk through is today there's actually 3 parts to 3D printing something. People like to talk about the 3D printers themselves, but that's just step 3. Step 1 is actually how do you even create 3D content? And normally it's with computer-aided design software, which is known as CAD. How many people here know how to use CAD? Right, okay, so that's way more people than town knows how to use CAD, right? I mean, most people don't know how to use CAD, and most people don't want to learn how to use CAD. It's like accounting software that's meant for accountants, right? CAD's meant for engineers. Most people don't want to learn complicated software. So today you have to use complicated software, and then this middle slide, the middle pane, is actually, it's called slicing software. So once you have your CAD file, basically once you have this drawn out in your 3D CAD file, you have to slice it up and generate a machine path that will actually make this on a 3D printer. That's kind of obnoxious software to use, and it looks like you're traveling back into the 90s as far as user interface. It takes a lot of trial and error to figure it out. And then finally, the last stage is the 3D printer itself. So there are 3 kind of difficult to use steps in order to get a 3D printer, or to get something 3D printed that you designed yourself. And that's probably honestly why most people in this room said they've never used a 3D printer to design something of their own. So this is what we're trying to do. As you'll see, there are still 3 parts. We're just making it a lot simpler. First off, CAD, gone. Don't worry about it. If you don't know how to use CAD, you're off the hook. You're not going to have to learn. We're going to bring really simple 3D content generation to you on a tablet. And I know a lot of people in this audience probably use tablets, but kids live on tablets. I mean, I have little cousins, and if you take them up to a just regular laptop screen, they'll try to push it around because they don't even understand anything that's not a tablet. Slicing software, nobody likes it, so let's get rid of it. Let's put it in the cloud. It needs a really strong, like beefy, fast computer, but most people don't want to own a really beefy, fast computer. They just want to have a tablet. So we'll put that in the cloud. We'll take care of all that need for high computer resource for you, so it's not a big deal. And then lastly, the 3D printer. It doesn't need to look so much like a science project. Maybe it looks a little bit more like a microwave. Kids can't reach inside and burn themselves. So anyway, so we're basically developing all 3 pegs of this stool. But to the consumer, this is what it looks like. It just honestly looks like a tablet and a 3D printer. They're both connected to Wi-Fi, and what happens in the middle, you don't really have to care about. And as an example of some of the things that have been made, I actually gave this to Craig earlier. So this says, I can't quite read it, it says MIT Enterprise Forum. I just made this today, this afternoon. So I just literally drew this on my tablet with my finger. This is my bad cursive. And anyway, that 3D printed out. My co-founder made a rocket ship the other day. Here's a guy rowing a boat. And that's our most basic kind of simple app that we're using for demonstration purposes right now. But we really imagine templates where it's not just kind of a two-dimensional object given a third dimension, but truly interactive 3D content generation, and then it's just a matter of pressing print and it prints out. So that's what we're going for, and this is kind of our vision, right, is the Easy Bake Oven. Now, most of us probably didn't need Easy Bake Ovens because our parents knew how to cook, but imagine if your parents didn't know how to cook, right? I mean, there's like a lot of parts of cooking. You got to go to the store, you got to buy the ingredients, you got to chop them up, you got to somehow not burn yourself in the oven. Well, Easy Bake Oven has literally been one of the most successful toys for 2 generations because it took all of these things and made it so simple and put it right in front of you. And I really believe that integration is what makes it easy, and that's what we're trying to do with 3D printing. And ultimately, it's because we believe that once you make something easy, it's just fun. And honestly, 3D printing is really fun. I 3D print almost every day, and it's really exciting. And I think that your kids are going to love it, and my kids, when I have kids someday, are going to love it too. So that's the vision. That's what Mission Street's trying to do. And lastly, I'll just say I did promise to tell you how 3D printing is going to change the world. Well, I think that you are looking at the people who are going to change the world with 3D printing, because technology doesn't change the world, people do. And someone said to me once, the definition of technology is something that you can remember not existing in the past. Well, for me, I can remember cell phones not existing in the past. But honestly, the personal computer, it doesn't feel like technology to me. It's always been there. For these kids, 3D printing is not going to be technology. It's just going to exist. It's going to be something that was always there. And they're going to take it places that we can't even imagine yet. And so that's why I think that 3D printing is going to change the world. What I'm trying to do is give each one of these kids and everyone of their age a 3D printer to use in their school and in their home, and then just step back and watch them do amazing things. Thank you very much.
Casey is a product of UC Santa Barbara. He had out of College of Creative Studies, which is a very difficult program. He had a double major of physics and mechanical engineering, went on to Stanford, got a master's degree in mechanical engineering design, has been involved in all kinds of technologies, too many that half of them I don't even probably know about, but they've all been things that are on the leading edge, things that are really complicated, things that have very high failure rates. And I've had the privilege of working with him on, gosh, let me see, 3 or 4 different customers with incredibly different projects, one for NASA, one for the Army Research Labs, even one for our good friends at the CIA. All of these were completely different, but in each case, Casey had the task of taking something from a concept to a prototype as fast as possible, as cheap as possible, and as efficiently as possible. So he's, I forgot to mention also, he's an instructor at UC Santa Barbara in the Mechanical Engineering Department, teaches probably the most popular class, at least among engineers on campus, and that's the robotics class, which is really just a fancy name for BattleBots. And you should go to the final exam. It's usually open to the public. It's fabulous. It's a competition. That's their final grade, is how well their robot does. So Casey has used and continues to use 3D printing in, as Brian said, its original sort of purpose, which is rapid prototyping. I'll leave it at that and turn it over to Casey.
My perspective is going to be a little bit different than Brian because I'm a user of the technology. As Craig alluded to, I try and do things every day that I have absolutely no idea what I'm doing. And so I have absolutely no qualifications whatsoever for almost everything that I try, and I'll show you some of that here. And so the only thing that I know is that I need to try as quickly as I can, fail as quickly as I can, and try again. So I want to use technologies like rapid prototyping to teach myself to become the person who doesn't fail at something, and I'm going to give myself and hopefully convince the current board of directors to give me 3 or 4 fails before they judge me harshly. So I'll talk about some history from that perspective as a user. And so if you're planning on using 3D printing for a project that you have, then you might be more in my shoes. And I'll talk about a purchase decision that I made for my company to buy or not to buy 3D printers. I've got a personal example, and then I got one slide on my thoughts on the future. So 3D printing, as Brian said, is a big tent. We've got additive manufacturing in there, and I've thrown the word automated in because technically welding is additive manufacturing, but that certainly doesn't count. And we've got SLA, we got FDM, and we got laser sintering up here. And I haven't interacted with SLA in like 10 years. Brian told us a little bit about how that works. You got this goo bath, and the laser comes along and solidifies the goo, and you're left with this ugly, brittle, incredibly expensive part. And I worked at a company in the Bay Area 15 years ago, and we gobbled these things up. And the reason that we would tolerate one plastic part that we were planning on making in mass manufacturing and costing $5, we're going to spend $1,000 or $2,000 on an SLA for that, is because we wanted to fit check it ahead of time. We're not going to spend $250,000 on an injection molding tool and then realize the part's the wrong size. And so that's some of the history of SLA, and it was incredibly expensive back in the day. It continues to carry forward because it has higher resolution than these other techniques up here, but really it's a rapid prototyping technique, and I don't think I've seen anything of any existence of people using that in the just in the overall marketplace. FDM, Brian talked about that. That's the sort of glue gun one. That's the one when everyone thinks of 3D printing. That's what you're thinking of. Lots and lots of cool plastic parts, almost all of this stuff, almost all of that stuff. FDM. As Brian alluded to, the cost has come down, the resolutions have gone up, they're cheap enough that you could actually buy one if you really want it. Like, it's incredibly cool. And laser sintering is worth talking about. It's been around for a long time, but it's getting cheaper too, and the big deal there, it's completely inferior to the other two with one humongous exception. It can do metal. And metal is important, and so laser sintering is going to be another up-and-coming thing. Inferior resolutions, higher costs, but metal. And so, I guess that's a little bit of background. It all comes down to cost. I've got pictures here of the way we traditionally make things. Got a milling machine and a lathe up there. And if you want to have a prototype part made, the go-to was always you send it to a machine shop, or if you've got one of these fun toys, you probably paid at least $1,000, probably a lot more for one of those. Then you can go and make these yourself. You buy a chunk of metal, you gotta own the machine or take the machine shop time, you gotta pay a skilled operator. If you're making something hard, machinists make a lot of money because making difficult parts is a really hard thing to do. I've certainly, I'm not incredibly old yet, but when I was 10 or 15 years ago, a rookie engineer designing truly terrible parts and sending them down to the machinists who've been doing this for 40 years, there are some rough guys who have some rough words for some young engineers that really need to be told that you're really screwing the whole thing up. And those guys are expensive. And material costs, right? We buy a huge chunk of material. We want it to be strong. We want it to be lightweight. So we turn 95% of it into chips that are on the floor that we sweep up and we throw away. And I paid for all those. Some of the really great things about 3D printing, the machine time dominates, and the machines are coming down in cost, which is awesome. There isn't a human operator needed for much of the time. We'll start the thing up, might need to do a material change, maybe not, but for the most part it runs on its own, and you only pay for the material you use. And Brian's example of using finite element analysis to optimize shapes is a great one. So materials. Shapeways is an online vendor that uses the tools like Peter makes, and they've got a whole pile. I've actually went looking through their website to try and figure out if they're actually doing laser sintering or if they're actually 3D FDM printing wax and then casting it, and I can't tell, so they don't want to tell us. But either way, they've got a whole variety of stuff. They've got plastic with aluminum dust in it, and stainless, and silver, brass, and bronze. Any of this stuff you can gold plate, sandstone in full color. They got food-safe ceramics, a whole pile of different plastics, including stuff you can make joints out of, and more being added every day. And the cost of this stuff, granted, you have to wait for it, right? The online vendors, usually you're going to wait a week, maybe 2, maybe 3, depending on what you're willing to pay for. But you can get access to the latest technologies really, really cheap. And we'll talk about that in a second. So I'm concerned about what can this enable? What does 3D printing make happen for us? What can we do that we couldn't do before? The cost is a huge one. Rapid turnaround is pretty cool, right? You have one of these things in your garage, you got a great new idea, and so you're gonna send it to the printer tonight, come back tomorrow morning, and provided you've done this enough, then you can have a relatively complex part, and we can turn things even faster. And so that's really interesting for someone like me, if I'm doing a mechanical project, to be able to turn prototypes as quickly as I can. If I can do 5 fails in a week, that means I can start today, and I can be done by the beginning of next week with my 5 fails, and maybe I got something that works for you. Personal and small-scale manufacturing, right? We can start doing production runs. I can tell you from almost every venture I've been in, we had grand plans to scale to manufacturing, and we started with a prototyping technique, and we were planning on, oh, we're only going to do that for like a month or 2. A year later, we're still running way too many parts in our prototype manufacturing because, oh, the overseas manufacturing didn't work, and you wouldn't believe that second round of shots out of the injection molded tool looks like potato chips all crinkled up. And so we can begin to extend this manufacturing ability from prototypes because it's cheap enough, carry it further out. That'll give the little guy, that'll give the designers real leverage over the vendors going forward. And we're going to talk about, I got that bullet point further down. And then mass customization. You're seeing that already in jewelry and in art, and it's going to start to come down to everywhere. I think one of the big things that 3D printing will enable is that we all can have the exact thing that we want. And you can think of that in terms of, oh, well, I want a specific piece of art that's completely original. Okay, that's fine. But for medical, for dental, for anything involving your unique human body, all of a sudden, the uniqueness is an incredible enabler. It's cheap, which is great, and then this is another one. We can make parts that we've never been able to make before. Right now, we're just thinking about using 3D printing to do what's already been done. Can I make a part that a machinist would have been able to make, but can I make it faster or cheaper? But we haven't even begun to explore this technology can do things that nothing could do before. And it has some problems and can't do some things that some other things are better at. But those other things we've already got. And a lot of the stuff that we haven't really figured out yet. It sort of feels like the internet in like, 98, right? This is going to change everything, and we have absolutely no idea how. And so we're there in this time of great excitement, and some really interesting things are starting to happen, but it's just the tip of the iceberg, and I can't tell you what's coming, but it's going to be awesome. Alrighty. Some stuff on the market, right? 3D printing is absolutely taking off. We have 30% annual growth, right? It looks like the Santa Barbara housing market for the last year. Expected to be a $3 billion market by 2018. Some of the big players are starting to jump in, right? You're seeing investments by companies like Staples and Microsoft and UPS, all knowing that somewhere, right? Staples wants to put them on the shelves, and UPS is thinking, well, maybe there'll be a bank of these things, and people will come in and do this instead of doing photocopies. And so when the big money is starting to come in, and they're waiting for the whole thing to sort out, and so it's getting good. And the early hit markets are interesting, right? The rapid prototypers and the designers, that one's not a big surprise. And the hobbyists, right, of course, starts with the open source project. That's not a surprise at all. The jewelry one caught me by surprise a little bit. That's been a runaway hit for people designing their own jewelry. And again, it seems like, well, as an engineer, how relevant is that to me? Well, actually surprisingly relevant, as you'll see in a second. But again, it's enabling technology that's doing something that we couldn't do before. And the last one really got me. One of the early runaway market hits is replacement parts. Oh, this little cheap 50-cent piece of junk in my dishwasher broke, and the company that made it went out of business, and they got bought by somebody, and then they lost the prints, and like, I've got it right here, right? It's too many parts for me to glue it. And so what people have done is they pulled that broken part out, they modeled it in CAD, they put it up on the web, and they're selling it for a couple of bucks. And all of a sudden, you don't have to scrap a dishwasher because one plastic part broke. You can fix it yourself, or maybe someone else has already fixed it for you. And so it's just the early hits, and there's things like this. I never would have seen the replacement part thing coming a million miles away. And there's going to be more and more little things like, oh yeah, of course, that are going to keep coming. So first of two little cases that I'll talk about is, again, my business, right? I'm go fast to try and make up for the fact that I don't know what I'm doing is sort of my company motto. And so I'd love to have a 3D printer. It'd be great to be able to turn things faster. And so about a year ago, I had the opportunity to say, all right, well how would we use this thing? We got a project that we're going to be printing a lot of really small parts, and so this could be a really great thing. And so I went on a search, and I needed to be able to print ABS, and most of the printers will print in plastics that are a little bit more environmentally friendly, a little bit less toxic, but aren't quite as thermally stable. And so I had a requirement there. And I wanted to buy one that had 2 nozzles. And the reason for that is that I had plans of making parts that weren't necessarily square and big on the bottom, that might have abstract shapes. And so if you have a second nozzle, you can print a sacrificial scaffold. So you print this little scaffolding, and then the part builds up on that scaffolding. And now I don't have to do a machine change when a material change, because I have 2 nozzles, one for the ABS and one for the scaffold. And so I decided on the MakerBot Replicator 2X. I had to wait for it because it wasn't available until September of 2012. It's been selling since then for about $2,800. Fit my needs. There wasn't a whole lot else at that price point. There was a couple of things coming in, maybe about half that cost at that time, but not a lot, and they didn't really suit my needs. So that was sort of the decision that I was coming to, and I decided not to. I simply decided to hold. And the reason was prices were dropping so fast, all these additional materials were coming around, vendors are popping up in town and on the web, and I could have access to all this technology. I could get someone else to run it for me, which I absolutely love. And I could basically wait this thing out. I absolutely know that I will have one of these, but the time is not right for me because it is moving so fast, and there's so many people that are buying these up and offering them as services. And so that's the thing that I decided to do. I'm going to wait this one out. And the only caveat to that is right now I don't have demand for it. I'm ordering a very, very small number of 3D printed parts per month, and that will probably stay that way for some time to come. However, if that were to change such that my volumes went up and I really needed to be turning parts a lot faster, right now I can afford to wait for a variety of reasons because, well, I'm in way hotter water with software and firmware and electronics on these particular projects than I am for mechanicals, so I can actually wait this one out. And so I think for me, for this particular evaluation, I'm waiting now until I have either the volume or I really, really require those fast turns. But sometime soon they're going to be cheap enough that I'm going to have to jump in. And so again, here's a couple of the online vendors that are doing this, and there are a growing number of machine shops and prototyping shops, both in town and in the sort of greater Southern California area, that are doing this. And that leads to a less than engineering example of something I've used 3D printing for. I'll frame it as an engineer because that's sort of how I frame everything. Engineering project. Make engagement ring for girlfriend. One of the design restrictions, have 0 jewelry design experience whatsoever. Figure, well, I'm lucky enough that she doesn't want to rock, which is great for me and probably good for the miners of Africa. And I wanted to make it unique and personal, and so I could put, we'll talk about the cost of the material, and I'd like to keep in mind when I tell you how much these things cost that my hourly rate is astronomical. So it's really, they really are expensive. It's incredibly expensive rings we're talking about here. That being said, I spent a bunch of time coming up with some personal imagery that would be very, very unique and special for our relationship and for her. And I know how to use CAD, which is great. Slaved away. I mean, I can tell you, trying to learn CAD now is a breeze compared to trying to learn it 20 years ago. But I'm glad that I've sort of have that in my past. And so there's a CAD model that I put together, and I don't do a lot of artistic stuff, so it was a bit of a reach for me to try and get my mind around the swooping surfaces and come up with the techniques to figure that out. I was using SolidWorks in this case, but I'm sure if you were Google SketchUp or if you have any of the other CAD tools, then that'll get you there as well. And so here is, of course, we're an engineer, right? So we're going to make prototypes, right? We got to have a round of prototypes. I took my calipers to her ring collection, and they're all different sizes. And ring sizing is just a giant sham anyway. And so then I'm like, and then she doesn't wear any rings on that finger because, this is a wedding ring finger. So I got nothing. So I made the ring a little big. I knew it wouldn't fit well, but I knew I'd be able to get that sucker on her finger when I asked. I knew she'd also appreciate the fact that it was a surprise, and she'd also probably understand that this isn't what you're going to be stuck with for the long haul. So here are two different of the prototypes, same exact design. On the left, we've got I think that's a PLA plastic, and on the right is aluminide, which is aluminum shavings inside a ring. And yes, I got my fiance a plastic wedding ring, but it didn't last long, which is good. So again, keeping in mind the incredibly expensive hourly rate that went into this, vast, vast sums of money. Anyone want to wager a guess? Ring on the left, ring on the right. Those are ring-sized, normal human finger. Hands, just throw out a number. How much they cost? $5. We have $5. Awesome. You're killing me. Anyone else? $5? 10, 20? She's not here. She said she was going to come, but she's got another meeting, so I think I might have looked at her. $3.70. We're going down from $5. Is this the Price is Right? I'm getting married here. Come on, you guys. Is that it? We got $3.75. Anyone else? Do I hear? No, really? Do I hear $7? No, I bought it, right? I paid for these. That's a picture of those suckers sitting on my table. $40. Okay, we're getting there. Each or one? Each. $40 each. Thank you guys. This is great, right? It's like, I mean, I guess technically as a consultant, I am also technically unemployed, so that would be infinite month's salary, so I passed that bar as well. So without shipping, the one on the left I think was $2.80, $82.83, something like this. The aluminide costs a lot more. I think that's about $3.20. They only do UPS 3-day, so it was like $6 in shipping each. So, this is Shapeways. Okay, so moderately skilled designer, never used CAD before, popped on the internet, got custom designed jewelry for $5 plus shipping. Plus we were going on vacation, so I had them shipped separately, so it's actually $12 in shipping. Okay, so you can guess what her dad said, right? A plastic ring? Okay, so not for long. So here is prototype number 2, properly sized to her finger after we had our happy moment. She was actually fairly eager to get on to generation 2, as one might imagine. Got to put a set of calipers on her finger, and more importantly on a ring that fits really well on that finger. Brought all the wall thicknesses down, resized the imagery, got it all right, sent it off in polished sterling silver. More expensive because it's polished sterling silver. Less expensive because this one, because of wall thickness and proper sizes, is actually about 1/3 of the volume of material of the other ones. Take a guess on cost here. You know that shipping is $6, so that doesn't count anymore. 25, 50, what do we got? $10. All right, this is actually 60. Sterling silver is kind of expensive. If you didn't have it polished and want to polish it yourself, it would actually be about $40. And so this is powerful, right? Not only did I buy a wedding ring for $60, but it's highly personal. It's one of a kind. It has imagery of our relationship. It is something that is unique and special to her beyond just spending money could ever be. And it's something that I did. I leveraged essentially only my prior use of CAD, which it's not that bad to learn. Other than that, I have experience. I guess I'm a mechanical designer, so there's that. But I had no jewelry design experience. And I was able to just sort of go forward and make this project happen. And there's no reason to think that anyone else can't do exactly the same thing, whether it's jewelry, whether it's replacement parts, whether it's something that you've always wanted to build, something that you've always wanted to fix. Right now, the limitation is it's probably going to need to be plastic, and it's probably going to need to be fairly small, and you'll expect that those limitations probably will start to fade away as the future comes toward us. So I'm going to throw some predictions up as well, and of course, predicting the future is a dangerous game, so don't hold me to these. It's going to start to show up everywhere. It's cheap enough, and that's the real driver. You'll expect that the guy who has a lot of tools is going to have one of these things probably inside of 5 years. You won't see them in every household in that time. Brian, I so hope your vision is amazing. So I hope that you win. You're right. Children and prototyping is it's a magical mix. So. You'll continue to see expansion into available materials, particularly metals. One of the things that I find particularly interesting is the ongoing integration of things. You'll begin to see integration of different materials. I'm particularly excited about making electrical and mechanical assemblies together. Can I have a mechanical part that has the traces of a circuit board printed right into it? So I've got the electronics and the mechanical become one thing. That's something I'm pretty excited about. It's not going to replace mass manufacturing, but it has already begun to change the way that mass manufacturing works. Everything will get 3D printed first. It will probably get 3D printed instead of in ones and twos, now in dozens and 50s and hundreds, and then go into injection molding and all of these. We've got these wonderful techniques that are expensive and great at producing thousands, tens of thousands, millions of parts. 3D printing won't replace those, but it will change the way, and already has, the way that those parts get prototyped and the way the beginning of that process looks. I threw up here, we're not going to be 3D printing food anytime soon. I do think the houses thing is really, really cool and has a lot of promise, but that's a ways off. I hope it's closer than I fear. But our limitations, cost has set us free, and right now our limitations are size and materials. So for little stuff, it's amazing already. And this last one is mass customization. I think once we get a taste for what mass customization is like and how everything can be custom designed for us, we will never be able to go back, right? There are all sorts of predictions about how, a 286 is the fastest computer you'll ever need, and a 56K modem is the fastest connection you'll ever get. And once we got a taste of those capabilities and the powerful platforms that people were able to put on top of that capacity, we refuse to go back. In fact, we demand more and more processing, and we demand more and more bandwidth, not because we care about gigaflops and megahertz, but megabits rather, sorry, but because of the cool platforms that vendors have put on top of it. And I think as soon as the mass market gets a taste of customization, not necessarily because they're 3D printing their own things all over, although that's a beautiful future, instead because of the custom design, specific for you, clothing, appliances, kitchenware, dental, medical, we won't go back. And so I think that 3D printing will enable that mass customization that will be so, so important. Thanks.
Well, Brian and Casey were just perfect setups for our third speaker here, Donald Park. And Donald's up to his eyeballs in 3D printing in a way that is absolutely integral to his business. And let me provide a little bit of background here. Donald Park is vice president of DenMat Holdings, which is a company located here in the Central Coast, Lompoc actually. I assume that stands for dental materials. And it's one of the leading companies in this area. Donald's whole background has been in additive manufacturing and 3D printing throughout the medical industry, biomedical as well as dental. Went out of order here, got his undergrad in physiology from McGill University in Canada, did his graduate work at Northwestern, the Kellogg School, has worked at several companies right in the middle of this field, Biomet, Strawman, Biomet 3 guy, all heavy-duty players in this space. So that, Donald Park.
So, confession, I am a techie. In my personal life, I love Apple products, but I'm also practical. So I just recently had to give up my iPad because I like writing notes. And, I don't like to buy Samsung, but unfortunately, this is the best writing tool. So in my work, I've been privy to a lot of different aspects of the medical and dental field. And I want to walk you through some of the things that I've been fortunate to be a part of in this space. So, there you go. So I'm going to cover 3 different areas tonight. The manufacturing technologies and materials that are available today for additive manufacturing, 3D printing, implants, and osseointegration, and precision components. And what I consider in the medical dental space, is called near net shape. They're not good enough to be final shapes coming out of these systems. So the technologies was mentioned earlier this evening, fused deposition modeling, FDM, laser sintering, direct metal laser sintering, EBM, electron beam melting, another technology that's available. DLP, digital light processing. A lot of these companies, including 3D Systems, have DLP systems or technologies. SLA, one of the oldest technologies in the 3D space. Materials. So in the medical field, materials that are being currently used, cobalt chrome, powders, stainless steel, titanium. There's actually machines that will build parts out of PEEK, polyether ethyl ketone, I believe it's called. Wax, which at DenMat we use a lot of, and also other plastics and resins. There's a whole slew of them. We're limited in our ability to make more parts based on materials. So if there was any of you out there that are looking at getting into space, develop some more biomedical materials that we can use. In the spinal space, these are actually spinal cages that are used in spinal fusion surgeries. We have a pointer. There we go. That's a spinal cage. These are extremities. They're actually renderings of fingers, finger bones that can be replaced. So these shapes, as was previously mentioned, cannot be made using traditional milling, casting, or injection molding. These are very complicated matrix structures that are put in so that bone can actually grow into the space to have a successful osseointegration to happen. Okay. Other examples of implants, this is an acetabular cup, a hip replacement, another hip cup for revision surgery, and a dental implant that are also being made using this technology. Now, you can't get this smooth surface using this technology, so it's in combination building these components out of laser-centered parts and then putting it onto a milling machine to complete the final product. But you have the best of both worlds. They have software available today, very complex software, that will help you design matrix surfaces that are applied to these parts to get the best osseointegration possible. So I spent the past 6 years in the dental space. I've already also spent some time working for one of the global orthopedic companies, but dental is where I did a lot of my work, especially with 3D printing. The dental industry, believe it or not, is one of the biggest users of this technology. You probably all know Invisalign. They're the largest users of 3D Systems SLA machines in the world. But the final aligners that are put in the mouth actually aren't made from 3D printing. The models that are designed using the patient's teeth movement over a period of a year or 2 years are printed, so you would have multiple models, and then you would have a polymer sheet that's actually sucked down over those models, and that's how Invisaligns are made. But this is a photo of a plate of laser-centered cobalt chrome structures for making crown and bridge, and that's where DenMat and I've been working a lot in is in this area. So the latest technology, which has actually been around for almost 30 years by a company in Germany called Sirona, they produce, and there's other companies out there, including Itero, E4D, and so forth. Instead of going and having a impression taken traditionally and biting down on this disgusting material, which our company sells a lot of, by the way, you can now take a camera photo, intraoral scan, that is digitally uploaded to a system, cloud-based system. We would receive it. We would digitally design the restoration. We actually print models. We would print or laser center the structure. You can actually see how good the fit is. It's uniform. But this is when it's all dialed in. This is when it's all working perfectly. But in the real world, it takes a long time to get all this dialed in perfectly. So a photo up here, this is how laser sintering works. It's actually a sheet of powder, and it's built up layer by layer. It's an example here of different portions of it. So when I mentioned near net shape, this is what you get out of the machine. These structures here above the surface of the structure or the framework is actually support material. So in order to build up in three-dimensional space and to have an even plane, support materials added. So this is actually upside down or right side up. We would then have to manually hand finish, cut off all those support material, polish it, apply porcelain, and our ceramists do that, to get you a final crown or bridge. There's other companies out there that have developed powdered gold and use this laser sintering technology to actually build gold substructures for making crown and bridge. And recently, there have been advances with craniomaxillofacial surgeons that are doing entire jaws out of titanium or cobalt chrome. So this is what we do at DenMat. We actually produce, we're the #1 patient-requested luminaire or veneer on the market. We do everything digitally. We CAD design smiles. We print on wax printers. These are all patient-specific, as the previous speakers call it, mass customization. This is the best technology to use for individual components. Milling, injection molding, it's still, depending on what parts you're trying to make, is still the fastest and cheapest way to make mass customized parts. But when you're talking about high volume customized components, 3D printing or additive manufacturing is the way to go. So we actually print wax patterns, and we use a traditional lost wax process, burn out the wax. We actually shoot it with molten ceramics, porcelain, or lithium disilicate, and we create the final restoration. So there's a lot of before and after shots. So we try to make people smile better, look better, and some before and after. So these patients could have taken up orthodontics, but they opted for a quick fix, luminaire, veneer, but we're trying to change people's lives by using this technology. So factors consider, how many people are looking at this technology to implement in their manufacturing? A few, okay. So these are things that you really have to consider, is look at what the systems are available out there and the capabilities, because they're all different, and you have to look at it on a product-by-product basis. The software is critical, and there's a few out there that will be able to help you design and output the products faster and better. How does it fit within your manufacturing workflow? Do you have to change a lot of things? Is it actually cheaper to implement this particular process versus another process or a system? Cycle times. This is actually a longer cycle time process for most part, because you're actually depending on how tall the parts are, it takes a long time to build those components up. Precision. So in the medical dental field, we're looking at precision or tolerances in the 150 microns for medical implants. In the dental space, we're looking at 10 to 20 micron tolerance or fit. And it's very difficult using this technology to get down to that level as of today. I'm sure it'll get a lot better, and we're hoping it does, because we want to be using that technology in our manufacturing workflow. So are you producing a final shape product, like a lot of the prototyping parts that don't require a lot of high precision for the most part? Or are you okay with producing near net shapes and you're going to do some finishing later on? So in the orthopedics field, when we're designing a custom hip for a patient, it took upwards of 44 hours to actually mill on a 5-axis machine a certain part. We were able to shorten that time down to 24 hours to do a 3D printed part or laser printed part, then put it on a milling machine for less than 8 hours and be able to reduce the cycle time. So faster turnaround time to the surgeon, and effectively would lower costs for the manufacturing facility. Serial customized production, as I spoke earlier, is the way to look at this technology, and then also consider the investment and the unit costs. So, this technology is great. We all get excited about new technology, but you have to be really thorough in your business case analysis to figure out, is this the right technology? And for the most part, for the medical device and dental field, it is, but it's not for every single component. I have some more examples here. This is a cranial replacement made out of PEEK. So there's a $1 million machine out there that can actually 3D print out of PEEK material. It's very high temperature and it's very expensive. This is actually a bone rasp for, people are squeamish, but for digging out or cutting out bone in your upper leg for a hip stem replacement. And this is sort of the complicated structures that you could ultimately creatively design using this technology. You could never mill that or injection mold that. This is only be able to produce using this technology. So I thank you for your time, and talk to you soon. Thank you.
So we have some backup slides that I'm going to run through. Actually, Ben Tucker helped me with the first set of these, and I wanted to share them. This is going to be a departure from the nerd talk for a moment here. You can see here, this is what we're depicting is the different companies that are active here, and the relative growth rates of a few. You see 3D Systems there, and Stratus is the two big kahunas here. And they've both been, I think they've both been seriously on the acquisition bench, which accounts for some of that market share growth. Well, I'm sorry, I can't read that. Hopefully you can. Go to the next one there. This is basically the growth of the market over time. Now, this one is an interesting chart. I remember reading or reviewing this one earlier. It has to do with public perception, and it's really interesting how the 3D printing compares with some of the others that you've all seen. So it's growing remarkably fast. In terms of the global potential, again, it's predominantly a U.S., predominantly a North American phenomenon, and as all three speakers emphasize, it's not going to take the place of mass manufacturing of common parts. It is a way to get very high customization parts printed cheaply and rapidly. And in that sense, we lead the world. This is a representation of the market here. Can I get there? Right around in here is where John Pototi and Bob Johnson tend to invest. And up in here is about where Craig tends to invest. But you can see 3D Systems and then the whole market for that matter have completely outstripped the general market, which is the brown or burgundy line below it there by hundreds of percent. So I like to look at these kinds of charts, not because I'm a great financial analyst, but because it kind of adds a little bit of reality to the business. Is this a hobbyist kind of a thing, or is this for real? And the amount of money, the amount of interest, the size of the market suggests it's for real. I think it was, I think Casey used the term 3 billion. Here we see 6 billion by 17, so I think those are consistent numbers, 3 billion right about now. Again, the trends, all very strong. The two biggest companies being 3D Systems and Stratus is shown on the lower charts, just growing like crazy. Here's some of the companies that are, well, these are the so-called pure plays in 3D printing. There's plenty of companies that are in 3D printing in a big way that aren't showing up here, like Boeing or some of the other larger manufacturers, where it's a small fraction of their business. These companies are firms where 3D printing is the core of their business and therefore representative of how the business is doing. And you can see their 1-year stock performance off to the right there. That far outstrips basically any asset class or sector that I'm aware of. I'm going to stop here and go into some interesting applications that were not addressed here specifically, but I think that they would be of just general interest. The first here is the use of rapid prototyping by Nike and Adidas. In the old days, or 2 years ago, it would take, according to Nike, 12 technicians 6 weeks to come up with a new shoe prototype. And now it's down to 6 people and 2 days to come up with a new prototype. So the impact on something as like the sneaker industry is just enormous in terms of their productivity. This is a case, this is actually, I believe it was Australia. a prosthetic hand is, round numbers, depends on, of course, the specific case, but it's typically about $10,000 a digit. And the problem with a young child is that he's growing. So you buy the prosthetic, and in a couple of years, at least, you're going to have to replace it with another and another and another. This particular device was made for $150, and it was really more by, he was an engineer, but not in the 3D business, 3D printing business. He made it on his own, and it's now basically giving it away on the internet to anybody that wants it. So this is kind of it's a great story. Well, we are back to Nerdville. This is a NASA rocket test, horizontal stationary rocket test. The most stressed particle in these tests, or one of the most at least, is the fuel injector. This operates in a 1400 psi, 6,000 degree Fahrenheit environment. It is just really, really gruesome. And in this particular test was the first serious application of 3D printing for such a high-value component in a rocket engine. And it performed incredibly well. NASA's absolutely thrilled with it and have plans to send a 3D printer to the International Space Station. The idea being that it would be better to make parts up there as they're required rather than trying to shuttle parts back and forth with a space shuttle. Very interesting. This is a fun one. This is that's a turntable, and I forgot the brand of the company. Does anybody know the name of this company that's doing this? It's really pretty cool. You put whatever you want on there, and it's got two lasers, and it automatically creates the 3D file and then prints it. So whatever is on there, you can basically recreate. And it's just amazing. This is a consumer level product. At MIT, they posed an interesting question, and that was, can you 3D print an airplane? And of course you can't. And MIT said, of course you can. And what you can do is 3D print the parts, and this is an approach very, very similar to the finite element analysis and then the removal of material that Brian and Casey both mentioned. And if you do that in an intelligent manner, you can 3D print the result, which, like everybody's already said, you can't possibly an injection mold that kind of a thing or fabricate it in another manner, but 3D printing makes it very easy and very cheap to do. And this is extremely lightweight, high strength. In this case, it's a wing structure. This is very interesting to me. This one is they're actually printing a liver, a human liver. Now, they're not printing the whole organ. I mean, that'll come, I'm sure. But they're actually taking liver cells and printing liver tissue in a manner that's exactly identical to living liver tissue. And you say, well, so what's the benefit of that? It allows pharmaceutical companies to test various drugs and pharmaceuticals on the liver. Almost every product that you see in the market says, they have that disclaimer that side effects might include kidney damage, liver damage, whatever. This is an easy, cheap, and safe way to test these products for such things as liver damage or kidney damage without having to use a real person. So, but we'll get to the point of probably a full printed liver or kidney soon. And then we have some materials I think you guys already covered. I won't go into detail here, but we're now seeing 3D printing in wood, ceramic, newspaper, concrete, salt, and it really seems to be no inherent limit anyway. And since we've got our next event coming up, I thought I'd mention a little bit about Kickstarter. There have been a couple of 3D printing projects that have been well funded on Kickstarter. Probably the most creative one was called Fuel 3D. It's a handheld scanner that sells for a 3D scanner that sells for less than $1,000, and so far they've raised over $200,000. Their original goal was $75,000 on Kickstarter. And then last slide, just to remind you, MIT, next event, MIT Enterprise Forum, will be at UCSB and on crowdfunding. Is the date up there? Yeah, November 20th. If you got any questions about it, we'll be co-sponsoring it. MIT Forum will be with Technology Management Program of UCSB, which is run by Mike Panessis. Just raise your hand, Mike, in case people want to talk to you about that event. Mike is putting together the speakers, and is Jim Semek here? Didn't see him. No, Jim and Mike are working it together. And with that, thank you very much, and we will open that up to questions.
3 quick questions here. The first of which is, it seems as though any of these developing sectors experience growth spurts when there are a lot of patents that come off protection. Certainly that happens in pharmaceuticals. And I think there was probably a patent spurt that happened about 2005 in this industry, and I was wondering if there's any group of closely allied patent expiration dates coming up that we could be watching for. Second thing would be the 3D printer that I owned recently suffered from the fact that it was extremely slow, 20 or 30 hours for large parts, and I was just wondering if there were any comments on where the speed issue is going. And then finally, the resolution issue, and how close are we to 3D printable optics, which is on the order of, a couple of 100 nanometers, 500 nanometer resolution.
Laser sintering, I believe, is coming off patent in 2014. That's one of the ones that you spoke about. The issue with patents is that they're very valuable, so as soon as you get one patent, the next thing you do is try to make a bunch of patents that are really close to it. And so even if the most basic patent expires, it could be that, for instance, it's like if someone had a patent on walking and they would then patent walking and chewing gum at the same time. So you can do the most basic form, but maybe you still have to wait a couple years before you can do anything in addition to that very basic form. So I don't know if we'll see an explosion in low-cost laser sintering, but that is the next big one to come off of patent. And I would also say, back to your Kickstarter comment, Formlabs out of MIT, that's an MIT spin-out, did low-cost SLA, citing basically that an SLA patent had expired. They were promptly sued by 3D Systems, and they, I believe, have settled. But it just goes to show that the big guys aren't messing around when it comes to patent infringement. So it's just something everyone has to be careful about if you're down on my level. Second question was speed. I can answer this one a lot more from personal experience. Basically, when it comes to FDM, that's the hot glue gun approach, which is the one we use. It's basically a heat transfer problem. It's how quickly can you put thermal energy into a solid bead of plastic. It basically looks like a really thick fishing line that comes into the top of this nozzle. It's heated up, melted, and then immediately it cools off again. So it becomes a heat transfer problem. Can you put a lot more heat energy into this nozzle faster? And if you can, then essentially you can just spit more plastic through that nozzle. So that's half of it. And the other half is, can you physically move that nozzle around at a faster speed? The normal, kind of a normal speed for a low-cost 3D printer as far as print rate is about 50 millimeters per second, I believe. So it's about 5 centimeters per second, or 2 inches a second. We've cranked up ours. We've gotten a better nozzle that can transfer heat faster, and we've taken a lot of the weight that's on the end of the moving carriage and put it somewhere else. And we've cranked it up to 175, so basically 17 millimeters, or what's that, 3.5 times as fast, and it wouldn't be able to print. And it's actually pretty extraordinary to watch. And I think that's just the tip of the iceberg. So I think that the speed issue will get solved pretty quickly, because you're right, it's obnoxious to wait like a whole day for something to be made. And on the third one, optics, I'll pass that to someone who knows better.
So I'd say that to raw print optics, you're going to be waiting a long time. But again, all the typical optical polishing methods will still work. So 3D printing could really offer an opportunity to say, okay, most of the optics materials seem like they could be readily 3D printed without too much trouble. You'll have to work through some purity issues to do lens work, but then a post-machining step and a polish, and you're in good shape. And I think that's one of the things that you're seeing a lot of with 3D printing is you start with 3D printing, take all the advantages of 3D printing in terms of lack of material waste, being able to do things that had never been done, and then you take them and finish them off with traditional finishing techniques, coatings, post-machining, polish, whatever else you need to do.
I just want to address the issue of actually designing these parts. I've actually looked into this myself, and I found it incredibly difficult to come up with any of these designs. Let's just take your wedding ring example for a moment. Suppose you were to design a wedding ring, but instead of making it out of $100 material, suppose it were $1 million material, and you really wanted to design it and had certain kinds of strength characteristics, flexibility characteristics, things like that. More along the lines of some of these medical applications. The software just simply doesn't exist, or at least in my opinion, it doesn't exist to actually do that in any easy to do way. And there's this, the problem is the software, the CAD software that exists was designed in an era when you were actually manufacturing these things with traditional machining. So the current CAD tools are just simply totally inadequate, at least in my opinion, for doing the 3D printing. Who in the world is working on both the physical shape design as well as the mechanical characteristics, both strength and flexibility and the things that you would want to be able to test for and simulate and model? Who's actually working on this stuff? Because I have just not found anything, in my experience.
I think I can guess that. So in terms of shape design, there's two software that I know of. One's German, called NetFab, and there's another UK-based company called Within, and they specialize in software for 3D printing or additive manufacturing. When it comes to finite element analysis, in the med device field, we go back to our traditional test methods and software and do the testing based on the systems that we have in place. Because we're governed by FDA and ISO 1345, we have to be able to prove and substantiate to the governing bodies that the density, the strength, and all of that has been fully validated. So from what I know, there's no software that does all of that in one package.
Yeah, I can jump in as well with maybe a cautionary tale and some of my experience. CAD tools these days, at least compared to the past, are easy. But engineering is still kind of hard. And the thing that makes a good engineer is you need someone who's smart, okay. Either you got that or you don't, you can work on that. You need some intuition and you need some experience. And 3D printing really lowers the bar to be able to let you fail faster and cheaper to get the experience and the intuition that will make you be a good engineer. I see it time and time again. In fact, here's the cautionary tale. I was a junior engineer. My first job out of UCSB was at Digital Instruments, a wonderfully successful, completely insane place to work. And one of the things that happened is that the company was basically run by the application staff. And the application staff reported directly to the customers. And so there'd be all these engineering requests. If I could just get 3 of these parts, I could sell 3 instruments, and that's $500,000 in profit. And someone else yelling the same thing about those parts and the same thing about these parts. Not very many engineers responded to these kinds of requests. I was a person with a list of about 50 little projects like that. One day, one of the PhDs, and I love making fun of PhDs, it's one of my hobbies, spent the weekend, came in and announced that he had taught himself the CAD software over the weekend, and ran around to all the other PhDs bragging about how he was free of the tyranny of the engineering group. And he proceeded to order $5,000 or $6,000 in parts from the machine shop. Not to be left behind, the rest of the herd of PhDs, about 12 or 14 of them in total, did the same. And we had over $50,000 in machine parts on order before the first set of didn't assemble, didn't work parts came back. That experiment cost the company over 50 grand. We had no functioning assemblies at the end, and no one would ever talk about it again, which is the reason I want to bring it up in a public forum. And so there's a lesson there that being able to use a CAD tool doesn't make you a designer, but using a CAD tool often enough and learning from your failures can. And so if you want to be an engineer, do not learn a finite element analysis package, right? It's, what's the expression? Computers are worthless, they only give you answers. I think that's Picasso. Finite element analysis will give you any answer in the world. And the parts of it that are really impressive are also not the parts that are very hard. And so I think that for the design examples, if you have very specific requirements about strength and flexibility, then you want to start with a quick calculation, do some simple strength and materials work. As soon as it gets complicated, then build it, and then test it, and then do it again.
You can buy a polymer printer for $100,000 to $200,000 now, and I assume that it's because the patent's ending that it's become reasonable for smaller companies.
I think it will take 5 years before laser sintering really comes down dramatically in price. My co-founder, who couldn't be here tonight, he did a lot of optics with lasers and these sorts of things in his PhD program, but he dropped out before he actually got the degree, so you can't give him trouble. We were talking about this just the other night about, someone's going to figure out how to do this, is going to figure out how to do laser sintering really cheaply. And we looked at the energy requirements, and he believes that the right group of people could make a laser sintering machine in their garage for a few $1,000s worth of parts. But that's a long step from, there's a long step between that and selling it to you for a few $1,000s. Just how long, you can attest to this. Product development takes a long time. So I think that within half a decade, yeah, you'll probably see someone selling a cheap laser sintering machine. I don't think you'll see it next year. I hope that answers your question.
So I just want to add to that. So if we look at the number of units being sold, I think that's where we see the scale being built with these manufacturers. There's Concept Laser, there's Phoenix Systems, there's EOS, there's MT, I forget the company in the UK that Renishaw just bought. If they're competing against each other in the same area. So the more they sell, the more they compete, the prices are going to automatically fall. So we'll see it come down, but not to the $50,000 level, because it's just very expensive technology. When you look at titanium laser sintering, it has to be done in an argon sealed environment. It's also very flammable, so there's fire suppression systems built in. So it's expensive technology, and there have been companies that have had fires even with stainless steel powder when they were cleaning the systems out. So it's still dangerous. People are using it. Is it going to get cheaper? It will. We don't know how much.
So I've always had a lot of fun making small things. Donald talked about some of the limits that he had run into, 10 to 20 microns for dental, which is pretty small. Where do you three see that going? And when are we going to get down to a point where we're bridging the gap with MEMS?
Sorry, bridging the gap with which?
With MEMS.
Okay.
Yeah. I'm asking for a swag, which Casey I know does well.
Yes. Yeah, you've got me stumped though, because you're going to have to bridge the technologies, right? Because MEMS is leveraging semiconductor fab. So if you don't know what MEMS is, but basically what MEMS is it's micro electromechanical systems, and so or structures depending on who you're talking to. And basically what it is it's to take the techniques that have been massively successful in producing semiconductor materials, like Intel is probably the most famous example, and say, well, let's make something mechanical. Rather than making a, quarter micron, living in the mid-90s, but a quarter micron transistor, instead we'll make a beam that is made of silicon because it's a semiconductor compatible material, and it will be 100 microns long, and it will be a half micron thick, and we can do all sorts of interesting physics with these tiny, tiny little mechanical structures. They actually exist in our lives. The airbags in your car are built on a sensor that is based on MEMS. That was the first runaway hit of that market. And so the bridging of 3D printing and MEMS, they are off right now by probably 5 orders of magnitude in terms of scale. So, the difference between 3D printing and MEMS in terms of resolution is, it's my body compared to the distance from here to New York or something like that. It's an astronomical divide. And And MEMS isn't concerned with getting bigger, MEMS is concerned with getting smaller. So I think that the thing that you will end up seeing would, again, as Brian talked about, be our ability to make tools. So I've followed and seen a bunch of interest in people making printed circuit boards, but not making photolithography masks yet. And so a photolithography mask is the tool that is used by a MEMS lithography machine in order to make a MEMS device. And so I think if you're going to talk about bridging that divide, I could easily imagine, and I've not heard anyone talk about this, but sort of like, my little MEMS kit, where you would 3D print a lithography mask, and you could, as long as you're not growing oxide, I think MEMS, you could do dirty MEMS in your garage, right? You can do etching, you can spin on photoresist, you can do photolithography. I wouldn't be surprised to see that come around. I've not thought of that, and I've not heard of anyone talking about it. So, Damon, you start a company, man. It's a great idea.
Digital Instruments is almost a fascinating precursor to try to do 3D printing at, not a contiguous scale. There would be 3D printing down to the tens of microns, and then there would be the kind of things that you would do with AFM probes. Are they doing that at Digital Instruments or at some of the other places, doing atom by atom 3D printing?
So I'm looking to Peter, who's shaking his head in the back row. I quit in '98, so that's the end of my Digital Instruments tour.
They tried to do something called dip pen lithography, in which they use the tip to actually print the oxide layer or the ink, basically a conductive ink, onto a substrate. The problem was that we had a lot of trouble controlling the movement of the tip exact enough in a vectored space like that. Because as Casey knows, we did a rasterized measurement with the AFM, and just about all AFMs use a rasterized scanning technique. But when you got to go through and do what you're talking about, it's got to be a vector-based. And that's very difficult to do, especially with the piezos that run most AFMs today, because it's all, extremely nonlinear and everything. So yeah, right. The company that was actually trying to develop this technology, I heard recently went out of business. So unfortunately, it's really neat technology and a really great idea to be able to just print out your circuit or your MEMS with an AFM, but I guess it's just not ready for prime time at this point.
Yeah, actually, to take one more cut at that, now that I've had a couple seconds to chew on it, I think that even using I've not heard of anyone using regular inkjet technology to try and do lithography printing. I mean, that seems like another bridge to the MEMS world, and it doesn't seem like a huge step as long as you're not doing, the hard things about semi, everything that makes it toxic and gnarly and awful and dangerous, have nothing to do with the mechanics. It's all about the doping, it's about the oxides, it's all about making the electronics. And so if you're doing MEMS, I don't know of a step in the process that you couldn't do cheaply. And I don't see why you couldn't use either a scaled up AFM, an inkjet printer, a very, very precise, expensive 3D printer to do some of the lithography steps. It would be a complicated operation, but I'd be willing to bet someone's going to give it a go, because, right, doing MEMS at home, that'd be pretty awesome.
Well, if there's more questions, I suggest we give the speakers one more round of applause.